So, title of today's talk is The Life History of Common Carp and how it can be used to control the species of wetlands and shallow lakes from the University of Minnesota. Out in general, we're going to talk a little bit about carp and common carp in particular. Then we're going to speak about the life history of common carp. This is in line with my philosophy that if you're going to control an invasive species, it's really best. In fact, you have to understand it in some detail. A little bit about the ecological damage it causes and why that's important to understand and how that relates to your particular situation. Three control options with some somewhat cherry-picked examples, but I think you'll find them interesting, and some conclusions. So carp. Carp are nothing more than large minnows that live in rivers of the family Cyprinidae. And there are about a dozen species actually that can be placed into three groups: Eurasian carps, Asian carps, of which I know you have some, and Indian carps. Today we'll be talking about common carp, which is probably your worst problem because they will sustain themselves, as will goldfish, in wetland systems, while the silver carp and bighead carp and grass carp need flowing waters to release their young. So we'll talk about the common carp today, which is just put a circle around it there to the left. Common carp is really a really interesting animal. It evolved in the Volga and Danube river basins, which feed into the Caspian Sea in Europe and in Eurasia, which hopefully you can see this here. And what's interesting is they migrate up and down that, well, here we see the Volga. Uh, Thinking about this river system a little bit, where interestingly, these fish are now actually somewhat threatened and endangered. If you look, and I've never unfortunately been there, but they're very large slow-moving rivers, quite similar to the Mississippi River. The Volga is 3,500 kilometers long, complex braided channels, many floodplains with wetlands, connected wetlands, harsh and variable, ice covered in the winter, hot and dry in the summer. So this is all really similar to the Illinois River system that you're working in. And interestingly, in Europe, there are many more cyprinid species, which do make a difference. And that's key, probably, to the invasiveness. But here we have a picture of the Volga and Emiquon, which you can see you really can't even tell them apart. So no wonder once the common carp was brought over here, which was well over 100 years ago, it did pretty well because it was at home. The life history of the common carp, as Pajemic will tell you in the talk after this, a little bit more detail. We've gotten into it in some detail, and it turns out it's quite interesting. It can be divided into four basic life history phases, and I'll talk about them a little bit here and then in a little bit more detail. So the first one involves egg deposition and spawning, which we see down here onto aquatic vegetation. The eggs hatch into yolk sac larvae that resorb the yolk within a few weeks. So this is a very brief, but actually very, very important time in the life history of this particular species. The larvae then develop into juveniles, which grow quickly and mature, and then they develop further, and this is a process in the fisheries world known as recruitment, and join the adult population. Looking at the adults, which I define as sexually mature individuals, they continue to grow, but they have some interesting movement patterns. They can immigrate and emigrate. They can actually typically form winter aggregations. And from those aggregations in the spring, they usually perform highly directed movements, we found, at least in Minnesota lakes, to very specific spawning grounds. What looks like chaos is actually pretty well organized in the world of the carp as synchronized events. And then after spawning, they may return back to a feeding area. This can take various forms in various rivers, large lakes, or even smaller wetlands. And the system just repeats itself. So a little bit more detail, and egg release is where we'll start. It's important to realize that mature females can have well over 1 million eggs, and they can spawn typically spawn at least once a year, but maybe even multiple times. This is very important. They're extremely fecund. This makes it very hard to control if they're having reproductive success. I just alluded to it, but mature females follow this movement pattern, which can either be very small in a small system or very large in a large system. In the Volga, migrating actually hundreds of kilometers, believe it or not, kind of like salmon. They will migrate from a winter refuge area, deeper waters, to shallow waters every spring to spawn. This can be highly synchronized and even involve homing. And then once in the spawning grounds, this is a system in Minnesota that Pojemek and I figured out how they were moving between these three lakes. Anyway, once in the spawning grounds, they compete for mates and they release their eggs and sperm onto floating and submerged vegetation. That's what you see here in an extremely synchronized fashion, actually synchronized by sex pheromones that we have identified. Once they've released their gametes, the eggs are very small, but in the millions, of course, or even tens or maybe perhaps hundreds of millions, and they're attached to vegetation. But what's interesting is they're extremely vulnerable to predation by smaller fishes, which are quite common in Europe and some areas of the US, but not everywhere. This is their most vulnerable life history stage because they're stuck to these plants, sitting ducks, kind of. And they will absorb the yolk after a few weeks and then start swimming. But during this phase, they're basically like candy to many small fishes with small mouths, like bluegill sunfishes, certain catfishes, certain types of minnows. And we have found that they can actually, in lakes with healthy micropredators like this, you can get 100% control of carp reproduction because these eggs are so abundant and these fish are so good at getting it. And this is just an example from a lake in Minnesota showing after 3 days, every single egg was eaten. And there were probably billions of them in that lake. Very important point. So don't just focus on the adults, think about the young. The juveniles, if there are any survivors, and of course, typically there aren't. That's why they have millions of year eggs, grow very quickly and seem to live mostly in shallow waters. They are susceptible to predation by things like gar and pike, but within a few months they are not because they grow so quickly. This is a picture actually from Pojemek here, showing within a year they were probably out of the gape size of most predators. If they make it past the juvenile stage, the adults are also extremely impressive. I've already talked about the precise and complex movement patterns. Now I'll talk about the resilience, how efficient they are at feeding, and I'll mention very briefly, they're actually pretty smart in the fish world. They have very well-developed brains. They learn and remember for many months, and acute sensory systems to chemical cues and sound in particular. So very impressive at that level, very impressive behaviors. They're physiologically quite resilient, long-lived, routinely living decades, and we've caught them up to 70 years old. And here's an obituary to a carp in the London Times about 10 years ago. Very long-lived animals. Again, they're formidable then if you leave a few females in the system and they're able to reproduce, right? And lastly, they're very, very efficient feeders with specialized mouth parts that allow them to pick and dig in the bottom. In the process, this is the problem. They uproot plants, free detritus and nutrients into the water system, releasing algae blooms and causing massive declines in plants and then insects and then waterfowl that feed on them. And here's an example of just such an effect in Hennepin Hopper, just lakes just to the north of you guys. And this is from Gary Sullivan. But here we see Hennepin Hopper, I think in the early 1990s, lots of aquatic vegetation, but within about 10 years, the common carp had infested, you see, and they got cleaned out totally. In 2009, Pojemek Beyer and I and the rest of the lab, with Gary's help, completed a study at Hennepin Hopper. And we actually determined the number and age of the carp present in that system in 2007. And then through some techniques, we were able to back calculate their ages. And this is very important here because This is from that paper in 2009. But you can see that as the number of carp rise up to 300 kilograms per hectare, which is about 300 pounds per acre, they reach very high levels. But somewhere at about half that level, there's a critical inflection point at which the vegetation cover collapses quite dramatically, as do the waterfowl and the number of species. So low numbers of carp are not a problem necessarily. High numbers are, and it's important to know then what numbers you have out there. So those are just some basics here. So now, obviously, the common carp, as I showed you, and you probably know from hundreds of dozens of studies, are very damaging. How can you control this particular species? There are three basic options. You can basically try and exterminate the entire population, nuke it with rotenone. I'll talk about that. You can try and remove adults with netting. All these techniques have been tried for well over a century, or you can use a fully integrated set of approaches, which I'm going to emphasize and which was highly influential to me. First, we'll discuss the rotenone option. This is again from Hennep and Hopper, and this is data shared from Gary, and I think presented at your conference a few years ago. So hopefully hopefully you remember some of it. But when Gary came to us actually in 2007, the density and abundance of aquatic plants in Hennep and Hopper had decreased dramatically and was a state of collapse. And we discovered that there were about 300 kilograms per hectare of common carp in that system at that point in time. And I just showed you a picture for that. To respond to that, once we documented how many darn carp there actually were, they completed a rotenone treatment, which you see here, draw it down rotenone. And it actually initially worked really well. It was a huge recovery, but then the system collapsed again. So this time they went out and they dug up the drainage tiles, which they thought the carp might be hiding in, and re-rotenone the system in 2012. And actually, it's come back and they have a new equilibrium. As far as I understand, talking with Gary, things are going really well out there now. So using these, although there are still a few carp. So the conclusions are that the rotenone treatment on its own really didn't have long-lasting effects. It hasn't in many other locations, poisons all the fish too. But combined with other things, it could be very sustainable. And that's, they reached some kind of tipping point. How about adult removal if you don't want to poison all the fishes in your system? Well, we've explored that too, and this is in a series of lakes in Minnesota published in Beyer and Sorensen in 2010 in Hydrobiologia, and again in 2021, actually, because I don't have that reference here. Lake Susan, Minnesota, highly interconnected series of lakes with wetlands and marshes in here. And we sought to enumerate first how many carp were out there. We blocked the entrance and exit to the system. We assessed the population and tracked adults. And then we we blocked it with these simple screening systems. And we did 4 large commercial removals till we had the population down to about 50 kilograms per hectare. And the vegetation came back remarkably. And it's almost 10 years later now, and it's still really good. So we pushed it over a tipping point of some kind. Probably micropredators are out there really abundant. The adults are blocked from coming in from other locations, and we've pushed it back down through adult removal. But this took, the lessons are, we have to block immigration. You have to stop spawning on site or successful spawning, perhaps with predators, and you have to have large removals guided by abundance. Lastly, I'm going to give the full bore approach here. A very interesting story from Lake Sorrel and Creston in Tasmania, Australia. This was a multi-step adaptive process. Common carp were first noted in a system of lakes. I went down there and visited. That's how I know this system pretty well. In 1995, they pursued a series of approaches. And in step one, they simply closed the lake to all fishing. It's pretty remarkable. They formed a work group. And then after having closed the lake to people, they closed the lake to carp. And they built screened You have a similar system in Animal Quantum, as far as I can tell, a screened system so carp could not come and go anymore. So they closed it off. And they didn't also want to infest adjacent waters. They then started large-scale removals in the late 1990s. Initially, this did not go very well, so they stepped things up and they did what's known, and I would recommend that you consider this if you're interested in getting rid of your common carp, a radio tagged program in which fish are radio tagged and tracked, and this is known as a Judas or trader fish phenomenon. It's used to actually remove invasive goats on tropical islands. And they were very quickly able to find that the carp weren't randomly distributed, as I was telling you before, but found in certain locations, even with winter aggregations in southern Australia, which is not a particularly cold location. So they could determine how many there were and where they were. And then they went back and they started blocking the spawning grounds with actually miles and miles of netting, which they combined with adult removal and liming the young. They then went on to perform population estimates and tracking fish as they hammered this population year after year after year, tracking them and removing them. This continued down till they got just a few fish. And in 2007, I'll show you the data in a second, Lake Crescent was considered totally carp-free, and in 2023, sorrel was as well. They're functionally exterminated. And what's really cool about this is they were exterminated from the entire state of Tasmania, which is about half the size of Illinois. So the conclusion for an integrated control system is it really can work. It has to be adaptive. It has to be science-based. You have to know how many fish there are, where they're going. You need to be persistent. You need to target just both adults and young, as I pointed out, removing the adults and shutting off all spawning opportunities and not allowing any more in. But even extermination is possible without the use of any poisons. So in summary, the common carp is a fascinating fish, but it has some really distinct weaknesses. It's larval and young egg stage, which is extremely vulnerable on plants just for brief periods of the year, if you know when and where to look. They can be an obviously enormous problem to wetlands. Wetlands are one of the most challenging types of systems to control. I know that. I haven't had much experience with themselves. Every type of system, though, is going to be different. And these are adaptive animals, and their biologies and ecologies will be slightly different in them. So what you really should consider is a multifaceted scientific targeted approach, quite a mouthful, in which you determine how many there are. You go for this either eradication or 100 kilogram per hectare limit. And it can work if you're at it and you persistently chip away at their different life stages. It does not necessarily require rotenone, because I know you're reticent to use that. It's a sustainable patient. You need sustainable approach, a lot of patience, and a lot of funding, long-term funding. But I think you may have that, and I encourage you to consider it and work forward. It's a very interesting and rewarding process. Thank you very much for your time.